Right. I've broken up the inverse function section into two videos. So the first one is just kind of definition and some basic examples, and then the second video will talk about how to find the inverse function and then how to verify that a function is the inverse function using function composition. So we say an inverse function of a function has an inverse function. We say a function has an inverse function if for each output there is exactly one input. We also call something that has an inverse function, we call it one-to-one, or we say that the function's invertible. So if we say if f of a equals b, then the inverse function a equals f inverse of b. So the inverse function would be that f inverse f to the minus 1. And to give you a little bit of a picture here, a is in the domain of f, and f takes it to its output of b. Now b is in the domain of f inverse, and it's going to take it, it's going to take it right back to where it started. So a function and its inverse are going to undo each other. The domain of f is going to be the range of f inverse, and the range of f is going to be the domain of f inverse. So that just means the domain and the ranges of f and f inverse are just reversed. I'll give you an example, Celsius and Fahrenheit equations. To convert from Fahrenheit to Celsius, there's the formula. I realize it should be plus 32 here. I'm going to fix that in just a minute. So if I want to convert something that's in Celsius, I'm going to plug it in here. I'm going to multiply it by 9/5, and then I'm going to add not 35 but 32 to it, and that'll tell me the degrees in Fahrenheit. There's a silly picture in one of the textbooks that have some guy in Australia and then some guy or some girl in I don't know, Montana or something, and they're both saying it's 40 degrees out. So the person in Montana is all bundled up, and the person in Australia is it's got shorts on and sunglasses and looks like they're ready to go to the beach, because 40 degrees Celsius is quite warm, and 40 degrees Fahrenheit is kind of cold. So we would need some sort of conversion so that we can communicate that 40 degrees in one place means something entirely different. So for this function, our input, we're going to feed this Celsius, and our output is going to give us Fahrenheit. So our domain would be the Celsius, and our range would be Fahrenheit. Now we can go in the opposite direction, and we can do Fahrenheit to Celsius. So the Celsius equation would be 5/9 times Fahrenheit plus 32. So we'd be plugging in Fahrenheit and then adding 32 and then multiplying by 5/9, and that'll give us our Celsius. So our domain and the range are switched. So now we're feeding input of Fahrenheit, and we're getting output of Celsius. So this is one of the characteristics of a function and its inverse, is the domain and the range are switched. Okay. So invertible. Invertible means, does it have an inverse function? So we're going to go ahead and look at an ordered pair here. And my cat here is trying to help me out here, so he feels like he hasn't gotten enough attention. So he's trying to distract me. So our input here looks like Fahrenheit. So 32 degrees Fahrenheit is freezing. In Celsius, that would be 0 degrees. If it's 68 degrees out Fahrenheit, it'll be 20 degrees Celsius. So now we can see that 104 degrees is pretty hot, and in Australia that would be 40 degrees Celsius, and you can see that yes, probably shorts and getting ready for the beach would probably be appropriate. Maybe they don't have as much humidity as we have here. And this is going to be invertible because each output has exactly one input. So if you tell me it's 40 degrees Celsius, you're not going to give me, oh well, it might be 104 degrees, or it might be 80 degrees Fahrenheit. That wouldn't make any sense. We wouldn't want something like this. So this is invertible. So each output has one input. Let's look at another example. Well, first I'm going to tell you what the inverse is. So the inverse is just you switch the x and the y, and then we'll look at another example. So this time we're feeding Celsius, and then we're getting out Fahrenheit. Okay. All right, and you see that this function, this inverse is a function. Each input has one output. All right. What about another example? Is this thing invertible? Does it have an inverse function? So what we're looking for here is, before we would look at each x value. Each x value should have only one output. Now if we're looking for, does it have an inverse function, we're looking at each output, and it should only be associated with one input. Now you see a problem here. 7 has 2 inputs, so this is not going to be an invertible function. So we're going to say no, output of 7 has 2 inputs, and it has inputs of 1 and 4. Now what I'm doing down here is I'm writing out what the inverse relation looks like. And you see input of 7 gives me output of 1, input of 7 gives me output of 4, so that would be characteristic of not a function because 7 has 2 outputs if we're looking at the inverse relation. So being 1-to-1, each input has one output, each output has one input, so there's a 1-to-1 between inputs and outputs. We can look at a mapping example. So we have a couple of states, and then I forget if the number of representatives is accurate or not anymore, but we can use it as an example. So it goes by population. So Texas is a little bit smaller in population than California, and we'll assume that Alabama and Arizona both have 9 representatives. So because Alabama and Arizona both have the same output, this is not invertible, because if you say, all right, which state has 9 representatives, you would say, well, it might be Alabama or it might be Arizona, and there might be some other possibilities. So I can't go backwards and tell you exactly what it is. So this would be not invertible, or does not have an inverse function. Because 9 has 2 inputs. Okay, now we're going to look at another question. Does the parabola x squared, is it 1-to-1? Also, does it have an inverse function, or does it have an inverse that is a function, or is it invertible? So I'll go ahead and graph it, and I'm going to say, hey, look, input of 2 and -2 both give me outputs of 4. So this would not be invertible, or it's not 1-to-1, or it does not have an inverse function. That all means the same thing, because the input of 2 and -2 give me the same output. So the output of 4 has 2 inputs. And notice I drew a horizontal line there. You see how it crosses twice. That might be something that we need. Let's look at another function, x cubed. Is it 1-to-1? And we go ahead and draw it, and we say yes. For each output there is exactly one input. We can draw a horizontal line wherever we want, and it's only going to cross once, or maybe 0 times. Well, this one, it always will cross it once. Okay, and that gives us what's called the horizontal line test. So it's kind of like vertical line test, except for this one, the horizontal line. So we say a function has an inverse function if a horizontal line can be drawn anywhere and it only crosses a graph of the function at most once. So at most once means that it could cross once or no times. Okay. And then when I ask you, does an even function have an inverse? Even functions are symmetric with the y-axis. So if you're symmetric with the y-axis, you are definitely not going to be one-to-one because of that symmetry there. Okay. So the next video I'll have how to find inverse functions given the equation, and then how to verify that two functions are inverses of each other.